In this video, we're going to look at something called orbital hybridization. This takes advantage of something that we looked at when we were looking at electron configuration. Namely, when we looked at the p orbitals, and I called them the p suborbitals, the px, the py, and the pz, we noticed that the electrons could kind of spread out across those suborbitals because the orbitals were degenerate or of the same energy. We can take that a step further in the idea of orbital hybridization to give the electrons more options as they're looking at forming bonds. And this is really how things form bonds. And it gives us an idea of how molecules take on their particular shape. So without further ado, let's get into it. So again, I said I wanted to talk about orbital hybridization. Okay, so with orbital hybridization, let's get it spelled out. This provides or sort of provides an explanation of the question of how electrons in carbon spread themselves out to bond with 4 other atoms. And it's not just carbon, it's any central atom that has anything else attached to it. Orbital hybridization is important. So let's talk about the electron configuration of carbon. So the electron configuration of C. All right, the way we did this was we had 1s2, 2s2, 2px1, 2py0, 2pz, 0. No, that's not right. Let's put 1 electron. That's only 5 electrons. We need 1 more to get to 6 electrons total, 4 of which are valence electrons. Okay, so this is the correct electron configuration for a single element of carbon. But when we're preparing carbon to bond with other things, let's go back to the Lewis dot representation. In the Lewis dot representation, we actually spread the electrons out. 1, 2, 3, 4, north, south, east, and west, right? That allowed us to kind of see where we needed to add atoms as we were arranging our molecules together, okay? So if we have the dots spread out, the dots again are electrons, spread out as much as possible, we could see how everything would kind of bond. Now you probably, if you've watched the last 2 lectures and digested the content, it's probably not a hard thing for me to sell you on that these dots are not arranged north, south, east, and west. In reality, they're arranged in a tetrahedron and they start to add things to the various sites of our tetrahedron. That gives us maximum separation. Okay, so the dots spread out as much as possible in 2D. We just show them as these 4 dots at the various, north, south, east, and west. I'll stop saying that. Anyway, but that's not reflected in the electron configuration. But the electron configuration suggests something else. It suggests that 2 of the electrons, right, are paired up in the 2s2, in the 2s orbital. So we have 2s2, right? And then we have 2px1 and 2py1. So my point is we have 2 electrons by themselves, ready to bond, and we have 2 electrons paired up, and then the 2pz orbital doesn't have anything. It can't offer anything towards the covalent bond. So one of the orbitals is filled. It doesn't need any more electrons. It's full. One of the 2p suborbitals is empty. It doesn't have any electrons to contribute. So 2 sites can't participate in forming a covalent bond. So how do we get 4 bonds? How do the orbitals go from this depiction to this depiction? And the answer is orbital hybridization. Okay, so what happens here? Well, the original orbitals around the carbon atom are the 2s, 2px, 2py, 2pz. These are, in other words, the valence orbitals. If we're going to get 8 electrons around that carbon atom, we're going to use these orbitals. We're not going to use the 1s orbital. It's not a valence orbital. It doesn't have valence electrons, okay? It's in a lower shell, not accessible to the outside kind of bonding sphere. Now, what I'm going to do just to make this fun, because hybridization is pretty fun, is we're going to invent what's called the hybridization machine. Okay, so we've got these 4 orbitals. Some are filled, some are half filled. One is full, 2 are half filled, and 1 is completely unfilled. I'm going to merge them together and then pull them apart. I'm going to merge them together into a superorbital, pull them apart into 4 separate, what we call hybrid orbitals. Hybridization machine, we're going to get orbital, we're going to get hybrid 1, and we're going to put 1 electron in it. Hybrid 2, we're going to put 1 electron in it. Hybrid 3, we're going to put 1 electron in it. And hybrid 4, we're going to put 1 electron in it. Okay, so we merged all of the orbitals and their electrons, and we pulled them out one at a time. And now what we can do is we can spread the electrons out evenly across these 4 hybrid orbitals. The 4 hybrid orbitals are degenerate. That is to say, they are of equal energy. Huh. Well, let's come up with a better name than the term hybrid. So naming hybrid orbitals. This is important. I mean, it's all important, right? But this we got to know. So when we're talking about naming hybrid orbitals, that's me coming up with a different word for hybrid 1, 2, 3, and 4. Instead, what we're going to consider is what orbitals were used. Okay, so again, my hybridization machine is completely made up, but I think it's kind of useful to see what's happening. So the carbon is sitting there, it's got its 2s, its 2px, y, and z orbitals, and it's thinking, how can I make this so that everybody's happy? Well, what you do is you push the s up in energy a little bit and pull the p's down in energy a little bit, so they're all the same. They're all the same. Now, the only way to do that is to push them all together, pull them all apart. We put 4 orbitals in, 1s and 3p orbitals, pull out 4 orbitals now that are equal. So what went into the orbitals? So we used, into our hybridization machine, we used 1 times an s orbital. We only had 1 available, and 3 separate p orbitals. I call them suborbitals. They are separate orbitals, okay? So 3 p orbitals. We use 1s and 3p orbitals. So we get, instead of an s atomic orbital, we get an sp3 hybrid orbital. Okay, so we put an s and 3p orbitals into our hybridization machine. The orbital that comes out is an sp3 orbital. That's just what we call it. It's some hybrid orbital, but we call it an sp3 because that's easy enough to remember. We used an s and 3 p's to get to that orbital. So that's point 1. We get an sp3 orbital. Now point 2 is how many of these orbitals do we get? Well, it's always the number of orbitals in, 4 in this case, equals the number of orbitals out. So we get 4 sp3 hybrid orbitals. So naming the hybrid orbitals, we always use the atomic orbitals names just in conjunction. It always starts with s, so it's s and then however many p's we used. The orbitals we're going to talk about right now are sp3 orbitals because we needed 3p orbitals. Sometimes you don't need 3p orbitals, and we'll look at examples of that. So that would be sp2 and maybe sp. not instead of sp1, we just say sp because chemists don't like to write ones, I guess. It's a thing. Okay, so we get 4 sp3 orbitals. However many orbitals you put in, you get that many orbitals out. They're all hybrid orbitals. They're all of equal energy. So if an electron has a choice, it doesn't care which one it goes into. But if one of them's half filled, we're going to keep, if one of them's half filled, we're going to keep it that way and move on to the next orbital. Okay, so what I'm saying is that we put into our system a 2s2, 2px1, 2py1, 2pz0 atom. And to prepare for bonding, we now have an sp3 1, sp3 1, sp3 1, sp3 1. Okay, so the orbitals all look the same. They all look the same. Okay. Let's look at another example. What about nitrogen? So nitrogen has 5 valence electrons. 1, 2, 3, and then we put 1 lone pair. What this is saying is that with a lone pair of electrons, that's the only thing that differs from carbon. We still are looking at a 2s, 2px, 2py, 2pz. All of those atomic orbitals go in and they come out as 4 sp3 orbitals. But instead of the electron configuration we had up here, okay, instead of this electron configuration, what we have is we've got one of those sp3 orbitals has 2 electrons. One hybrid, and what type of hybrid orbital is it? It's an sp3 orbital, has 2 electrons. And that is our lone pair. And you could do the exact same thing for oxygen to show that it has 2 of these hybrid orbitals are completely filled with 2 electrons. So the hybrid orbitals are just like atomic orbitals. All they want are 2 electrons. They want to spread the electrons out as much as possible. So if you have a choice between 2, 0, have one orbital with 2, one orbital with 0, and both of them with 1, spread them out so they both have 1. That's better for everybody if you can spread out like charged subatomic particles. Okay, so they're just like regular orbitals. They just have weird names, sp3. We don't really designate the shell number because it's always the valence shell that we're worrying about. And the number of orbitals that we get out equals the number of orbitals that we put in. Okay, so something else that people like to talk about, and it is helpful, is the shape of hybrid orbitals. Okay. So what it is it's sort of, to get to the shape of the hybrid orbitals, it's an average, and it's, by average, I mean a weighted average, of the shape of the atomic orbitals used. Okay, so if I take my 2s orbital, which is just a sphere, and I add it to a 2p orbital, and I add it to a 2p orbital, worrying about whether it's x or y or z is going to complicate things. That's not what matters. It's the shape that matters, plus another 2p orbital. So again, one is x, one is y, one is z. That just confuses things to worry about that. Okay, they're all just 2p orbitals. And we're going to mix all of these atomic orbitals together through hybridization to give us 4 orbitals that look like this. Okay, and we can even put 1 electron. Okay, my point is there's a large lobe and a small lobe. It's a large lobe and a small lobe. Okay, so one of the lobes, it looks like a p orbital is my point. It's a dumbbell-shaped p orbital looking thing, but it's absorbed that s character, and the s character is just a big ball. So it's kind of like, you could think about it as all of the orbitals basically just got a little bit fatter on the top, okay? So one of the lobes is a little bit bigger than the other lobe, okay? And what we say is that they have 25% S character and 75% P character. Now, where am I getting these numbers? And how precise are these numbers? Well, we put 4 orbitals in. 1 was an S and 3 were P's. 1 was S, 3 were P's. Okay, so that's where I get the math from. So what fraction of the orbitals, that the total number of orbitals used, 4, what fraction were S? 1 of the 4. So 1 divided by 4 is 0.25. Turn that into a percentage, we have 25%. Okay, so 3 of them were P, and 3 as a fraction of 4 is 0.75 or 75%. So that's where I get these numbers. So the shape is, for all the hybrid orbitals we're going to look at, the shape is a distorted P orbital, a distorted dumbbell shape that has one lobe that's bigger and one lobe that's smaller. I mentioned before that we're going to look at orbitals that have that require fewer P orbitals. So if there's an sp2 orbital, for example, we only took 2 P orbitals. So it's, think about the math, 33%, 1/3 S, and 67% or whatever P orbitals. What that means in terms of the shape is that if you computed this thing on like a supercomputer and looked at the actual density of the electrons, the big lobe would be much bigger because it's more S character or more spherical. I don't want to go into that detail. It's all just a distorted P orbital, distorted dumbbell shape with a fat lobe on the top. Okay, so we've looked at the shape, we've looked at the percentage of S and P character, we've thought about how these things are made. One thing I'll just mention in terms of how these things are made is, when does hybridization occur? Now, this is not at all, this is a good question, but it's not an important question, if that makes sense. Like, it's not a question where knowing the answer is going to get you places in life. But when does hybridization occur? This is one of these quantum phenomena that hybridization, that is going from atomic orbitals to hybrid orbitals at the valence electron level, that happens immediately before bonding. That's it. So as soon as there are things that can bond to our atom of choice, it will then do hybridization very quickly. I mean, these are quantum phenomena, quantum mechanical phenomena. Electrons move very quickly. So it just happens quick. It happens quick. They rearrange themselves. They make themselves ready for bonding. It's kind of like, oh, atoms are coming. We got to get ready. Got to clean the house, hybridize the orbitals, make sure we have room for bonding. Okay, so let's look at hybrid orbitals and bonding. So we're going to now do some actual bonding with these hybrid orbitals. So recall that covalent bonds form when atomic orbitals overlap to make molecular orbitals. Okay, that's a pretty true statement, okay, and I stand by most of it. All right, make molecular orbitals. What we want to do is just add a caveat. So when atomic orbitals or hybrid orbitals overlap to make molecular orbitals. So it could be atomic and or hybrid orbitals. So for example, we had hydrogen. We've done this before, and it has 1 electron, and that 1 electron's in a sphere around that hydrogen. That hydrogen's sphere represents not the nucleus, but the 1s orbital. If we mix that with another hydrogen in a sphere with 1 lonely electron, what we do is we allow those things to merge. And then we conveniently, though it's not true, we conveniently draw the electrons as sitting now in the Venn diagram shared space of the 2 orbitals. In reality, when orbital overlap occurs, we then move away from the idea of an atomic orbital and we get into a molecular orbital where the two nuclei are fixed at a set position and the 1 electrons are free to roam about the entire cabin of this molecular orbital. And this is another one of these phenomena where as soon as the hydrogen atoms get close enough, the molecular orbital forms. There's no intermediate state where you can actually see the two orbitals overlapping and the electrons locked in small areas. Okay, we can do the exact same thing, except now we're going to use a hybrid orbital. Okay. So using a hybrid orbital, I'm going to start with a simple case of a hybrid orbital with 1 electron, and this is going to be an sp3 hybrid orbital. And let's let that interact with one of these hydrogen with a sphere orbitals with 1 electron. So when they interact, what we see is that our hybrid orbital, which is this distorted dumbbell, and I always like to draw the little tail pointing towards the sea. You'll see why that is in a second. In the hydrogen, we have this sort of artificial for the sake of discussion, but it's helpful to see how this bonding thing occurs. We have this overlap. It's actually helpful to stop at the overlap stage, but I'll draw the molecular orbital just this one time. So we have this overlap, and when we have an overlap, we have a covalent bond. Remember, this is not a real state. As soon as we can, we form what is now a very complicated molecular orbital, where the 2 electrons are free to roam between the carbon and the hydrogen. Don't worry that the carbon is not being engulfed by the hybrid orbital. It's definitely a part of it. It's just the picture gets kind of nasty. Now, I actually like to stop here, not in terms of me talking, but in terms of drawing pictures. I like to stop at the overlap state as opposed to moving on to the molecular orbital because things get complicated. Okay, so let's draw the bonding for methane. So with methane, we're going to have 4 hybrid orbitals because we're ready to bond. And I'm letting that small lobe get really tiny. And these 4 orbitals are going to spread themselves up as much as possible. You guessed it, in a tetrahedron. And now drawing a hybrid orbital as a wedge and a dash is very difficult. So we're not going to do this often. But to each of these hybrid orbitals, we're going to attach a hydrogen. And let's keep, this picture is going to be gnarly already. Let's keep the electrons out of the picture. So that's CH4 bonding with its hybrid orbitals. When we have the hybrid orbitals, we don't have a sphere sitting in the middle of the carbon, and we don't have 3 lobes occupying the X, Y, and Z, those p orbitals, okay? We don't have p orbitals and s orbitals at the valence shell of our atom. Instead, we have 4 orbitals that all look identical to the incoming hydrogens. They don't care. They're going to find a way to get to that overlap. Now, something kind of fun emerges when we look at overlapping 2 carbon atoms, hybrid orbitals together. So let's make a CC bond. Now, it turns out that CC bonds can form in a few ways. We can have CC single bonds, double bonds, and triple bonds. And in every case, we're going to involve hybrid orbitals. But let's start with the simplest case. If we have a C orbital with its hybrid orbital, a C atom with its hybrid orbital, one of its 4 hybrid orbitals, and we bring it close to another C atom, we're going to let the 2 big lobes overlap and the 2 little lobes stick out near the carbon atoms. So the big lobes overlap. This is how we form our bonding molecular orbital. We allow the bigger lobes to overlap in a carbon-carbon bond connection. Not the little lobe with little lobe, not little lobe with big lobe. The little lobes are not involved in a bonding molecular orbital. It's the big lobes. Okay, so we're really creative about the anatomy of a hybrid orbital. We've got a big lobe, and we call that a head and a little lobe, and we call that a tail. And this works for all hybrid orbitals. You know, it's kind of weird to assign a head and these animal features, but I guess if you draw it right, it doesn't kind of looks like a fish. Okay, anyway. So we've got our fish orbitals, hybrid orbitals with heads and tails. And what I'm saying is that when carbon bonds with carbon, we're going to have overlap of the heads of each of the hybrid orbitals for each of the carbon atoms that are now bonded to each other. We get head to head overlap. Head-to-head overlap of hybrid orbitals is called, another hugely important term, a sigma bond. Forms when a covalent bond arises from head to head overlap of hybrid orbitals. Now, for those that are curious, and if you're curious about this, I'm impressed. But also, not just hybrid orbitals, also atomic in the case of H. Okay, that is to say that up here, this is a sigma bond. Oof, I don't like writing the word sigma. I've been doing it. We do not do it that way. Instead, we use the Greek letter for sigma, which looks like this. Okay, so that's a sigma bond. Also, this is a sigma bond. Now you might be like, but that's a head of a hybrid orbital and then just a sphere. It's like a fish eating an egg or something. Okay, that also counts as a sigma bond in this context. So, sigma bonds are another important term. So sigma bonds are strong covalent bonds. Really, they're the strongest covalent bonds. A really good technique, a really good thing to be able to do is count all sigma bonds in a molecule. So I'm recommending that that's what we do. I want to be able to give you molecules and have you count the number of sigma bonds that are present. So let's just start with this. All single bonds are sigma bonds. All single bonds are sigma bonds. Okay, what does that mean? I have this, and I said number of Greek letter sigma bonds. You would come back and you would say, oh, 1, 2, 3, 4 bonds. Okay, sorry, didn't mean to be rude right there, but yes, you've got the carbon-carbon bonds, but let's also remember the carbon-hydrogen bonds. Kekulé structures are not as fun as I remember. So we have those 4 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 4 is 16 sigma bonds total. And that's because we count those carbon-hydrogen bonds, yes. Okay, so it's a pretty long chat. Finishing up hybrid orbitals. We finished up hybrid orbitals and we looked at sigma bonds. Again, sigma bonds are the strongest covalent bonds that can connect two atoms, but they're not the only form of covalent bonds that can connect two atoms. We also have what's called pi bonds. And that's going to be the subject of the next lecture.